Hello and welcome to my video, lesson 7.5 on fission and fusion. So we're talking about fission and fusion. Fission is when we have a nuclear bomb. That's most of what we do is fission. Nuclear bombs, nuclear reactors. This is what we know how to do fairly well as humans. This is when we split an atom into two smaller atoms. Usually we're shooting an alpha particle at a large nucleus like uranium and have it split into two smaller elements like barium and kryptonium and release energy. Sometimes it's also going to be decaying, like maybe there's an alpha decay or something else that's taking place, or sometimes it's into just two very much smaller elements, like this case. Okay, and it also releases energy, and we'll talk about why in a bit. Fusion, on the other hand, is naturally occurring in stars like the sun and is used in hydrogen bombs. Fusion is much more powerful, but it only happens with extreme heat and pressure. So you have to really squish and force the atoms back together and to be able to fuse a bigger atom. So hydrogen, if you put two of these hydrogens together, a deuterium and a tritium, the two different isotopes of hydrogen, they can create helium. Okay, so this is the common formula for fusion, the most common. So both of these nuclear reactions release energy. Why? Because of the loss of mass in the situation. Now, if you look at the nucleon number, we have 236 at the beginning here, and if you count all this up, we still have 236. Down here we have 5, and if you count all this up, we still have 5. 4 plus 1 is 5. So the nucleon number doesn't change, but we do have energy being released, and there is a loss of mass. This loss of mass comes from the binding energy of the atoms prior to and after the nuclear reaction. And so this mass change is not very much. It's not even the mass of one proton or one neutron. It's much, much smaller than that. We're going to talk about the mass defect in a future video, but it has to do with that binding energy, the mass defect. And so what we're going to look for in these questions is how much is changing from one to another. So here it says uranium-235 is split into germanium 75, and what other product must be produced, and then if that product is produced, how much energy is released in the reaction. So what I'm going to do here is just make sure you can see everything. You have a whole bunch of values here. Those are not in your formula sheet. You're not expected to memorize these values, but if it was a test question, you would be given a bunch of values, just like I am here. So I recommend you pause the video now and try to figure it out yourself. Good luck. All right, uranium-235, and if you look on your formula sheet, it has proton count of 92, is split into germanium, which 75. Hold on, let's see if we can find it. Yeah, it's GE in your formula sheet, and it's 75, and it says it has 32 protons. That's what it says on the periodic table in your formula sheet. So if that's true, what other product must be produced? Well, it's going to be another element. So what we're going to do here is go 92 minus 32 to get our new proton count here, 60, which is neodymium, ND. Okay, and we're going to do the same thing with the mass number, so 235 minus 75, and we get 160. Which is too high for neodymium, but that's okay. So that those are the two options. Let's see here. All right, so I just thought about it a little bit longer, and this doesn't really make a lot of sense. And you won't be able to find the energy released because you don't have enough data. But the reason why it doesn't make sense is because this there you go, wasn't switching. This atomic mass up here is way too high. So probably there's a bunch of neutrons that are also being released. I don't know, 10 neutrons or something. Or if we were so nice, we could have 14 neutrons released, which would, if that were to happen, this would be 146, in which case we could use this number to be able to find out the mass of this thing. But we don't even have this one either, so it just kind of all goes out the window. So we can't actually solve this any further, but you should be able to say that it is neodymium that is produced in this equation. So what we're going to do is try another two questions here, ones that hopefully we can solve. So example number 2, pause the video now and see if you can solve it. In some of the largest stars, eventually they begin to make iron, well, that's not spelled correctly, iron 56 in their cores. What is produced when 2 iron 56 nuclei are combined in nuclear fusion? So this only happens at the kind of very late stages of a sun's life or a star's lifetime, because this takes a lot of effort. Basically, it has to be really squeezed together. Is energy being absorbed or released? So basically, we're going to start with this. Okay, and the element produced has a mass of that. So let's just figure out what element it is. It's going to be 26 plus 26, so 52, which is tellurium, and it's going to have a mass of actually, well, this number here exactly, right? Now, I mean, it'll have a count of 112, but realistically, it's actually going to have a little bit less than that. So what we're going to see here is that there's going to be a change in mass. Okay, that change in mass is going to be whatever mass final minus mass initial. In this case, mass final is 111.917 U, and the initial mass is 2 times whatever iron 56 is. So right here, so that's 55.934.938. Okay, so it's a very stable version of iron, like this. And so what we're going to do is figure out that number, and then we want to figure out how much energy is being or absorbed or released. Well, basically, the question is this number bigger than or smaller than the 11.917? And it's smaller, so that means we have less mass at the beginning and more mass at the end, which means energy has to be absorbed. So this is really important. Energy is being absorbed here. So if we take 11.917 minus this, it tells us our, it tells us our change in mass. which is 0.047124, but this is U, atomic mass units. So we want to convert that to grams. So we're going to use our formula sheet to do so. So we're going to times by, so that same number, but times by 1.66 times 10 to the exponent negative 27. Yep. So we get 7.8. We'll keep all the sig digs in our calculator, but times 10 to the negative 29, I think. Yep. Now, energy equals mass, change in mass, times speed of light squared. So energy is going to be that same mass number times by 3 times 10 to the 8, which is our speed of light, but we're squaring that. And so we get an answer of 7.04 times 10 to the negative 12 joules of energy. Now, this is joules. Oftentimes we're kind of expected to switch this into mega electron volts. So what we're going to do is divide this number by the conversion to electron volts, which is 1.6 times 10 to the exponent negative 19. So now we're in electron volts. So 4,400,2035. Is that correct? Yep. But now that's electron volts straight up. What we want to have is mega electron volts. So we're going to take that number and divide by 10 to the 6. So we get 44. Yeah, we're going to have one more sig dig. 0.0 mega electron volt. Why do we have only 3 sig digs when we have such a big number to start? Well, the speed of light is 3.00 times 10 to the 8. So we only have 2 sig digs for the speed of light, so we should only have 2 sig digs for our answer here. All right, and example 3, pause the video now and try it yourself. Okay, so for example 3, because the masses are actually given to us already, it makes it a little bit easier, and it's given to us in grams, which means we don't have to do as many conversions just to kilograms, which is a little bit nicer. So what we're going to do is add up all of these masses on the right side. So 139.9106 plus 89.9077 plus 11 times 1.0087. And so the right side is 240. Oh, hold on, it's not coming up. 240.914. And this is our mass final, whereas our initial mass was 241.0569. So it has changed, not by much. It never really changes by much, but 241.0569 minus this number here. And so we get a change in mass of 0.1429 grams. So that means our change in mass in kilograms is 0.0001429 kilograms, or 1.429 times 10 to the 4 kilograms, negative 4. All right. So this is what that looks like, but now what we need to do is put it into our equation. So change in mass times c squared equals delta mc squared. So we're going to take that number, so 0.0001429 times by the speed of light, so 3 times 10 to the 8, and then square it, and so we get an answer of 1.286 times 10 to the 13 joules. So there's a lot of energy being released because there was a lot of mass change, right? Because this is grams, remember, this is not atomic mass units. Okay, so that's a lot of energy being released, and we can probably just leave it there. Well, we should talk about sig digs though. 3 sig digs like the last question for the same reason as the last question. All right. I hope that this makes a little bit of sense. I hope the video helped you better understand fission and fusion. Fission is when we split an atom, fusion is when we put it together, and in both cases we either gain or lose mass, and because of the classic equation E equals mc squared, that mass, if we lose it, means we have to gain energy to make up the difference, or if we gain mass, we have to lose energy to make up the difference. So we're either gaining energy or losing it in the atom to make up the difference. I hope the video helped, and good luck.